que eu tenho que esperar ali. Tem mais 1 minuto e meio para começar a gravar. Não, pode ficar cedinho. Okay, sorry for the delay. Good morning, everybody. So this is the second lecture of our mini course. Still, we are going to talk about basic things. It's not easy, but necessary for the next 2 lectures. And I would like, starting, recalling some definitions and results that Bruna told us on Monday. So just to remind, all the algebraic method to understand things that we are going to do in the next lectures. We need the contact group. The contact group, as we've seen, is the set of diffeomorphisms of that kind, of that type, and the action is on the graph. 2 germs are K equivalent if this diffeomorphism, capital H, takes the graph of F into the graph of G. And Bruna has defined it, and she even showed us example of how to calculate the tangent space. I would like to say a little bit more about this. Well, we have this notation, theta f. Theta f means vector fields along F. But we can identify with ONP, the module, the ON module of germs from Kn to Kp, Kn to Kp. And also, we can see there this notation Tf Mn theta f or Tf Mn. Sorry. Here is n, theta n. So here we can identify this with J of f. J of f, here especially, is the submodule of ONP generated by the partial derivatives partial f x1, partial f xn. So it's easy if we do this identification, so in order to calculate. Another thing that appears there is this F star. What is this? This is the induced homomorphism. When you have F from Kn to Kp, for us, K means R or C, then you can define this F star from OP to ON in the following way. Is the F composed with phi. So when you look at F star of MP, we know that MP is generated by Y1, YP. Y coordinates in target, X coordinate in source. So F star of Y I is equal to Fi. So we can write this tangent space like this. So for this notation, I mean the submodule of ONP generated by the partial derivatives of F. Here it's an ON submodule, but here we take the coefficients in the maximal ideal. And here also, I1 IP, I mean the basis of ONP. And here is the extended tangent space. Okay? And also, and this is what Bruno have defined, the K codimension and K codimension. Also, here. Okay. Sorry. Sorry. I'm so sorry. Okay. Thank you. Sorry. CN to CP, CP. Okay, thank you. Sorry. Okay. And also, she defined this local algebra, and I just put here in this, using this notation here. So one important thing about the K group is that this tangent space is a submodule of ONP. It's a simple algebra structure. It's easier to work, for example, comparing with the A group. Okay. Oh. I think, no, okay. I thought I had some more definitions. Bruna also defined the A group. And we've seen in the first part last year of this mini course that two germs, if two germs are A equivalent, they are K equivalent. And we need this result for this edition now. Just to remind you something. So you have F and G from Kn to Kp. So if F is A equivalent to G, then F is K equivalent to G. A means we have change of coordinates in source and target, so that G is psi minus 1 composed with F composed with phi. Just right here. Here is psi minus 1, F, phi, and here is G. And so, let's look for some examples. Consider this germ that Bruna worked with Monday. Okay? Let's play a little bit. Take G1, for example, x squared plus x to the k. K bigger than 2. So we've seen last year that this, we can change coordinates in x so that this G1 is equivalent to x squared, y squared. It's an easy change of coordinates in x. So it's A equivalent, then it's K equivalent. But we can look at the algebra also. The algebra is there. So is O2. Let's look just the ideal. F1, F2. Or G1, G2. G11, G12. So here we have x squared, y squared. And here we have x squared plus x to the k, y squared. And then we can write here as that x2 plus x to the k minus 2, y squared. And this one, well, yes. This is an invertible element of the ring. So this is the same as x squared, y squared. So they are K equivalent because the algebras are the same. It's not necessary. The algebras must be isomorphic, but they are the same, so they are K equivalent. So let's play. If some, for example, you put something like that. Okay? Then you can look at the ideal. Oh, sorry. G2 of xy, x squared, y2, plus x to the k. All right? So this ideal is the same as this ideal. So in fact, they are K equivalent. Well, now, let's do something more complicated. G3. For example, x squared plus y to L, y squared plus x to the k, and you could put something more complicated here. L and k, for example, bigger than 2. It's not easy. Even if you look at the algebra, sometimes it's not so easy to see if they are K equivalent or not. Even for A equivalence, okay? We could do something more complicated, but that's complicated enough. So, can we say that G3 is K equivalent to F? That's I told this because I want to introduce the concept of finite determinacy. That's the main goal of this lecture. So what means finite determinacy? You take a germ in Mn, ONP, and you look at the k-jet. K-jet, for me, means the k-jet at the origin. So you just take the Taylor polynomial of degree k and drop off the constant. And then we have this jet. And we say that F is K, I put R, it's better, R, K determinant, if for all G, all germ G, so that the R jet of G is the same as the R jet of F, then F is equivalent to G. Okay? Well, we've seen that it's hard to calculate by hand this equivalence. Okay? So it's not simple by hand, just with this definition. Say if a germ is K determinant or not. Well, if there is such an R, we say that F is R finitely determinate, K determinate. Well, everything here is concerned with the K group. So I think I will press it and just say the words. Okay. And these are, we call the degree of determinacy. Then we have this nice theorem. Oops. Wow. Okay. We say that F is finitely determinate if and only if the K-tangent space contains some power of the maximal ideal, if and only if the K codimension is finite, we define this, if and only if the K codimension is finite. Well, okay, but we just say that's finitely determinate. That means there exists certain R, but which R? Is it possible to know this degree of determinacy? So we have more things here. If is R determinate, then the tangent space contains Mn R plus 1, ONP. Okay. This gives us some estimative, but this is better. If the tangent space contains Mn R plus 1, ONP, then it's R plus 1 K determinate. And if the codimension is D, then it's D plus 1 determinate. Well, let's just look at this result here. TKF contains Mn R plus 1 ONP, then F is R plus 1 determinate. But then we could use Nakayama's lemma, and write this like that, plus Mn R plus 2 ONP. Suppose this is true. It's easier when you have this during the calculation. Then you use Nakayama's lemma. Then you get this, then you get this. So this is a nice property to verify if some f is r plus 1 determinant. I really tried. I thought of different examples, but I kept it with this one that Bruna started looking at. So let's go back to our main example, x squared, y squared. Okay? Let's look at the tangent space. So this is M2, the submodule generated by the partial derivatives. So the partial derivatives are 2x, 0, 0 to y. Okay? Plus, what we have here? What we have here is O2, and then we are looking for this Fi Ej. So we have x squared 0, 0x squared. This F1 E1, F1 E2. And then Y2, 0, 0, Y2. Bruna did this already, but just true. No. Oh, goodness me. I will finish my lecture.
Excuse me, Roberta. I think in the use of the Nakayama's lemma, the Mn r plus 2 should go on the other side, on the left-hand side. No? It's Mn.
Oh, yes. Sorry. Oh, goodness me. Okay.
It's Mn.
Yes. Sorry. I wrote like that. Okay. Thank you, Juan.
Yes, okay.
Thank you. I should keep more attention to my notes. So here, one can see that this is, in fact, M2O22. Because, just remember, M2 is generated by x squared, xy, y squared. Then we have x squared and y squared. And then we have xy and xy. Okay? Exponent. M22. M22. Thank you. So it's 2 determinant. Then you can conclude that G that has the same 2 jet. I don't remember if I put L in K or whatever. If K and L bigger than 2, this has the same 2 jet as F, so it's equivalent to F. Okay? All right. So we've seen this already. So this is a nice geometric criterion for finitely determinacy, and Juan will show you how to apply this. And if a holomorphic map germ has finite k codimension, if and only if there's a representative which is finite one on its critical set. Critical point means not the derivative, not surjective. So this is a very interesting geometric idea. Okay. The other thing that we will need is this recipe for stable germs. Although I'm not defining what is a stable germ, well, we have several definitions. For example, we have the infinitesimal criterion that's TAE of F is ONP. then F is stable. We can define stability in a geometrical way. If you slightly perturb the germ, it remains equivalent to it. And you can define, as Cidinha will talk about, the deformation theoretic approach. This means that the Versal unfold is trivial, okay? So you can define in several ways and show that everything is equivalent. Okay, and then we would like to construct stable germs in the following way. This is not good. So let's start with this germ from K to K, okay? Then we have this normal space. We have this normal space here. Let's calculate it. So the tangent space is, here everything is an ideal. So I just write as an ideal. So this is x2, okay? I mean in O1. And then this normal space, we can write R or K. Let's just write R. It's O1 over X2. Then this is R, 1 and X. Okay? Okay. So this theorem tells us the following. So we have this normal space is a K vector space, and you take generators of this vector space, and also you consider the constant. You drop off the constant, and you can write this germ here. Okay, so you take the basis as a vector space of this quotient. You drop off the constant, and what remains, you put in here. And then you have this F, big F here is a stable germ. So it's the following. F of xu, because I'm going to drop this one. Then we can write x to the cube plus ux, u. So this is a stable germ from R2 to R2, K2 to K2. And you could do for all AK singularities and so on. You can always do like that. We start with some F, and you construct a stable germ from that one. So if you put here x to the k, then you go k plus 1. Then you go up to x to the k minus 1. Okay, because the derivative will be x to the k. All right? So here is x to the k, x to the k plus 1. And then you have this y1, yk minus 1. So is x to the k plus 1, y1, x up to, oh, goodness me, not feeling that. Sorry. Okay. And this is a stable singularity in the equidimensional case. All right. I don't have much time. Should I say something? No? I'm not sure if I should do this. Because we are thinking that Matthias would... is he here? Oh, sorry, I didn't recognize. Are you going to talk about this on your course? Yeah. But you can do on singular, okay? Okay. What do you think? Just quickly? Well, we said Monday that the algebraic approach is for classification and the study of invariants was provided by the K group. So we need a little bit of classification, okay? In the end, one important tool in classification is the complete transversal. So I'll try just to spend 5 minutes or less. Okay. And then another thing is that soon you will be able to assess the notes of the course. Then you have everything there carefully written and proved and so on. Then you can just look at the notes. So here I just give you a quickly flavor of this. Yes. Oh, all right. Okay. Also in the exercise slot. So here's the following. The classification is always like that. You do in the jet space, then you prove that's finitely determinacy, and then you go to the germ, to germs. And then we are going to look at jets from Kn to Kp of degree K, and we have this age K as homogeneous K jets. And then this theorem says that start with a K jet and suppose that this subspace of homogeneous K plus 1 jets is contained in T plus. What is written here is the jet version of the tangent space, but you see there is a square here because in order to apply the theorem, we need that the diffeomorphism has one jet's identity. Okay, so that's the reason we have this M2. So this is the tangent space in the jet space. And then any jet, any K plus 1 jet that has the same K jet as sigma is equivalent to sigma plus tau. Tau is a subjet, an element of T, and T is called the complete transversal. Quick calculation, very quickly, is the following. Let's start with this K jet. I'm going to consider it as a K jet. Okay? Then we have to calculate this tangent space here. Just this here. K1 means that where? Ah, yes, there is a mistake here. Thank you. It's T. Thank you. Okay. So this is the tangent space to this K1 group. K1 group means that the diffeomorphism has one jet equals to the identity. Okay. Then I have to calculate this. This is M22, 2x, y, 0, x, plus M2, x squared 0, 0x squared, xy 0, 0xy. So we are looking for all monomials of degree k plus 1 in each entrance. So T is actually as a vector space generated by y to the k plus 1, 0. Because we have y to the k plus 1 here. If you multiply by y to the k plus 1 here, this we can drop off. And here we have, but in the first entrance, we don't have. So this is the complete transversal, and sigma is an inner jet equivalent to something like that. Sorry. I think we should do this in the exercise. Okay? And then we can take A is equal to 1 if A is non-zero. And we can also prove that this jet, in fact, is k plus 1 determinate. So we have germs from K2 to K2. Sorry, I think I have to start here so Sidine can have more time. Questions, comments? Thank you, Juan and Gaffney. And Wojtek.
So I have a comment I want to make, and that is, if I was an algebraic geometer, I might wonder why we were bothering to study K equivalence. It's true that Bruna showed that there is an equivalence between K equivalence and the isomorphism of the varieties defined by the maps. But I think what Roberta has shown here is that because we're looking at maps and K equivalence, we get to use the infinitesimal methods to be able to show that we have equivalences. We could not really look at a family of varieties and construct equivalences, but when we have the maps, we can do some algebra, we can use things like Nakayama's lemma, and then we can show that this whole family of maps is K equivalent, and so the underlying sets are also isomorphic.
Okay, thank you. Thank you. More questions, comments? No? Okay, thank you. So I think we have just 5 minutes, and it's up to you. 5 minutes? Okay, 5 minutes, then
Por cima, isso. Uhum. Calor ou não? Nada. Ok. Melhor assim. Não. Não, tá bom. Okay, good morning. I'm Maria Aparecida Ruas, for those of you that don't know me. And so we continue with the curse of Isis. And so let me first see where we are up to now, okay? So from the lectures of Roberta and Bruna, we know the following, right? We know that if we have a complex algebraic set in Cn, in the neighborhood of the origin, right? And if this set is defined by one ideal, which is generated by F1, F2, Fp, where the Fi are germs of holomorphic functions at the origin. And if we know that P is the codimension of K in C of X in Cn, then up to here we can say that X is a complete intersection, right? And if we say even more that in a small neighborhood of the origin, the only singularity of X is 0, then this altogether gives me an ISIS. X is an ISIS, okay? On the other hand, we can associate to this ISIS a map germ from Cn to Cp, whose coordinates are exactly the generators of the ideal I, F1, Fp, right? And we know that we can study these map germs using the K equivalence. And Roberta gave the geometric criterion of finite determinacy. Yeah, she said that a germ is K finitely determined, a complex germ is K finitely determined if and only if the restriction to the singular set is proper and with finite fibers. So if I take a very small neighborhood of the origin, then I can say that F is K finitely determined if and only if F is K finitely determinate. If and only if the zero set intersects the singular set in a small neighborhood of the origin, just at the origin. Okay? So then we are saying, but what is F inverse of 0? This is X. And we have then the bridge between the theory of ICES and the K equivalence of germs, F1, F2, Fp, where these are the generators of the ideal defining the X. Okay? So what we are doing in this lecture is to study the infinitesimal methods of singularity theory, of mappings, in such a way that I can use them with an important tool to study ICES. When we are doing this, when we are doing this right side of the board, we can use both real or complex functions. So I can take, to develop this part, you see that we can, as Roberta already did, and we continue, we can consider both real and complex singularities, okay? Well, I will try to be very slowly at the beginning to give the main ideas, especially for the people that are taking the first contact with singularity theory. So the subject of this part of the lecture is to study K-versal deformations. So then I can ask, why to study deformations, unfoldings and deformations in general, right? So just as a motivation, if we look at this, será que eu consigo isso aqui? Mas ele está ligado. Tem que ser solar, né? Okay. So if I look at this wire bent in the space, so this bent wire, and if I look in this tangent direction at this point here, the view is this curve with this cusp singularity. But if I turn the head to the right or to the left, then the views change, right? So we can find either this picture or this picture. So I can say, if I look at this as a family of views, then I can understand much better the singularity. So this is the idea, and this is one of the most important tools in singularity theory that was proposed by René Thom, right? Perhaps the best contribution that singularity theory of mappings left to mathematics and even to science. Okay. So this is, as I already said, right? We can understand much better the nature of the singularity. Well, this in this lecture, if I have time, I will give the definitions of unfolding deformations with a motivation in terms of a finite dimensional model, and talk about theory of deformations of germs under K equivalence, and give some applications of these ideas in order to classify astable singularities. Okay. So before going to K equivalent unfoldings with respect to K equivalence, let's look at the finite dimensional model just to get the ideas. So suppose G is a Lie group, and acting on a finite dimensional manifold, and let me denote by Gx the orbit of X at X, right? So the idea of an R parameter unfolding is just parametrization of a slice of the orbit. So I'm mapping F, I'm mapping X from KR to M, such that X at 0 is the point X. So this parameterizes an unfolding of the point X. So this is the blue here in my picture, right? And we can introduce two basic concepts looking at this finite dimensional model, which then we will develop in the case of K-versal deformations. One is the concept of transversal unfolding. So I say that this unfolding X is transversal if it's transversal in the natural sense, or in other words, if the image of KR by the differential of X plus the tangent space to the orbit of X at X gives the whole tangent space at point X. Of course, if you have any question, you may ask, okay, please. The most important concept is the concept of versal unfolding, which is the following. An unfolding is versal, and look at this blue again. If for any other unfolding Y, I can show that Y is equivalent to an unfolding which is a pullback of X by some change of parameters. In other words, an unfolding is versal if any other unfolding, Y here in my picture, can be understood by some family that lives inside the blue slice, okay? Okay. And then the main result of the theory is to be able to prove that an unfolding is versal if and only if it's transversal. So then I have a good criteria to verify if a given unfolding is versal or not, right? Notice that if I have M, my manifold is a linear space, and the codimension of the orbit is C, then we can define a versal unfolding of X as an affine slice passing through X. So if the codimension is C, you choose a basis B1, B2, a system of generators B1, B2, BC, and you can write the versal unfolding exactly in this way. So an affine slice passing through C, okay? Okay, so now let's go to our, the main object of this. So I want now go back to the germs and define the main concepts in this setting. So then, let F be a map germ from Kn to Kp at 0, and as I said, we can consider both K being R or C. And when K is R, my germs are smooth, and when K is C, they are holomorphic. So an R parameter unfolding of F is a map germ with R parameters, so F prime, from Kr to Kn and Kr to Kp, of this form, such that when I take the parameter equals to 0, I get that f of 0x is f of x. So to go from unfolding to deformation, I just forget the parameter u in the target. So f prime is the unfolding, and f is the deformation. Okay? So F from KR to KN0 to KP is an R parameter deformation of F. So let's go over, so I have one example here. For instance, if I take the function x2 plus y3 that defines a cusp, and we can embed this function in this two-parameter unfolding. For instance, so when u1 and u2 are 0, I go back to my f. And we can see that taking different values of the parameters, we can get different views of my plane curve for fixed u1 and u2. And we will see soon that this unfolding, in fact, is the versal, this deformation is, in fact, the versal deformation of the cusp. Okay? So I let this exercise here. So if looking at this family, to prove that for u different from 0, the corresponding element of the family has a double point if and only if u1 and u2 are in this curve. So just to go back to the definitions we had seen in the case of finite model to see what we have here. So we have that two R parameter deformations, F and G, are K equivalent if there exists a germ of diffeomorphism phi in the source, right? But phi has to be an unfolding of the identity. In other words, phi is a diffeomorphism that preserves parameter. So phi 0x is x, such that this condition holds. This condition says that the induced isomorphism sends the ideal of G into the ideal of F, which is a condition that Bruna proved that corresponds to K equivalence of G and F, but with a special K equivalence that preserving unfoldings. In other words, equivalence of unfoldings, we give isomorphism of the corresponding elements of the family. Okay? When I say unfold, you forgive me, it's deformations, okay? I will try to, I'm sorry. So two parameters, okay? So, okay, so we said that an unfolding deformation is K-trivial if it's equivalent to the constant unfolding. Okay, and we say that a map germ is K-stable if any deformation is trivial. Okay, so now I have to define, I have to define what's the concept of versal. So suppose that F then is a deformation of little f. And first I will define what is a change of parameter in my unfolding, right? So given any h from Ks to Kr, I define the pullback of f by h in this way. H star of f is the unfolding, is the deformation given by f of hvx. In other words, I made the pullback of f by changing the parameter. We can also say that this map germ is base change map. So then we say that f is versal if for any s parameter deformation g of f, there is a change of parameter in such a way that G is equivalent to H star of F in the way I explained it to you in the finite model before, right? So, and we also say that it's mini-versal if there is no versal deformation with less than R parameters. So it's the minimum number of parameters for a versal unfolding. And of course, we can give the definition of isomorphism between versal deformations when my base change is a diffeomorphism, so between the same space, right? Okay. So the question is how to verify that a given deformation is versal. Then we have a criterion that, like in the finite model I gave before, will be based on the fact that an unfolding is versal if and only if it's transversal. Then I have to see what is the meaning of being transversal here, right? So I have here the expression of the tangent space, the extended tangent space of K equivalence. Roberta noted that we can use both the notation theta F for the set of all vector fields along F, but we can also use ONP as she used, right? So this is tangent space. And we have the codimension. K codimension, which is just the dimension of this space. Notice that this is, in a sense, the dimension of the normal space to the extended tangent space, right? Oh, so the theorem we have is the following. An F deformation is versal. Sorry, let me first say the following. Given this deformation with R parameters, I denote by Fi dot the directions of deformations. In other words, dfu, derivative with respect to the parameters ui at y equals 0. So these are the directions of deformations, right? And so the result says that the R parameter deformation is versal if and only if this condition holds. In other words, this vector space generated by the directions of deformations with the sum of the tangent space to the orbit gives the whole space. In other words, this is a transverse slice to the K orbit. Okay? Notice that this condition is good to be verified, so we can verify this condition. And so we have our criterion to decide whether an unfolding is versal or not. Any question? Any remark? Okay. Huh? Yes, Terry?
Do you want to mention how this is exactly the statement that the map given by the unfolding is transverse to the orbit?
Yes, yes. So this condition says that the map is transverse to the orbit, right? So in fact, when we have an unfolding satisfying this, we say that the unfolding is transversal. And this theorem says that the two notions are the same. So a deformation is versal if and only if it is transversal. But this say more, right? It says that when I look at this quotient is generated by a finite number of directions. And we know that if the codimension is finite, the germ is finitely determined, and vice versa. So in fact, we can state that the condition that F has a K-versal deformation is equivalent to say that F is K finitely determinate. Okay? Okay. Let's see one example. The previous example, in fact. So if I have my little f x squared plus y3, then this is the versal unfolding of it. Why? I compute the k-tangent space. In this case, this is very easy because it's a function. And then the k-tangent space, it's written here, down here. This is Jacobian ideal plus the ideal generated by F. But since this singularity is weighted homogeneous, it's easy to see that F, in fact, belongs to this ideal. And then we have this equality here. Then this quotient, a basis for this quotient, can be chosen as y and 1. And then, in fact, F is the K-versal deformation. I think I will skip this example because otherwise I may have time with we can look at it. So it's the example that, in fact, was considered by Bruna, by Roberta, and by Anne and Matthias too, right? So, but computing the tangent space and computing the normal space, I find the elements I need to write the expression of the K-versal deformation. Any question? Okay, so this was the important result then of this first part of this lecture, which is to show that K-versality is equivalent to K-transversality, right? And with the consequence we can get from this. From here to the end of the lecture, we go then to look at the relations between K-equivalence and A-equivalence, okay? So now we want first to look how to go from A orbits, so A equivalence to K equivalence. And I take any germ of rank R. So let's take a germ of rank R. And by change of coordinates, we can write F in this way, right? If it has rank R, I can write in this way, where U is U1 to UR, which means that F can be, we can think of F as an unfolding of F0x, of little F0x. And this little f is a germ from Kn to Kp of rank 0. So in other words, any f of rank R can be thought as an unfolding of a germ of rank 0 in this way. Okay? And of course, we will assume that little f is K-finitely determinate. And what I'm saying here is that given any germ of rank R, I can associate to it the germ F that is unfolded by big F. Okay, so I want to understand this correspondence in more detail. First of all, we have this proposition that I will not be able to discuss the proof. I intended to, but you see, I'm already late. So I'm not have time to discuss the proofs. But this one is so easy that we can give a look. So it says, suppose that you have two germs of rank R, F and F prime, right? And then you have little f F and little f F prime, which are the rank 0 germs unfolded by them, right? This result says that if F and F prime are A equivalent, then the little f and little f prime are K equivalent. And we use the previous lectures by Bruna and Roberta to quickly prove this. Because as Roberta said, if F and F prime are A equivalent, then they are K equivalent, right? And if they are K equivalent, their local algebras are isomorphic. But the local algebra of Q of F is written here, which is clearly, we can see, it's isomorphic to this, which is the local algebra of little f F. And then similarly, we have the same thing for F prime. And hence, as these two local algebras are isomorphic, then the other two local algebras are also isomorphic, okay? And then the germs are K equivalent. So, in fact, I have a correspondence between A orbits to K orbits, right? And as I said, we want to understand this map in detail. I think my lecture goes until it's 10:05, right? This, I think, yeah. Okay, so I have, okay. So let's look at this example to see, this example here, I would like to make it in the blackboard, because this example, in fact, is a preview of what we will do next. So then I put here, let me put the whole slide, and let me go to the blackboard. So as I said, we start with a germ of rank R, right? So I start with a germ of rank R, with rank 1, in fact. I write U, X, Y, U, F, U, X, Y, where F, U, X, Y is X2 plus Y3 plus U, Y. Okay. We don't know, we will not justify at this point, but you can trust me, this is a stable germ in the sense that Roberta defined that the A tangent space is the whole space, okay? So, but this is a rank 1 germ, and it unfolds the germ that I obtain when I take U equals 0. So it unfolds this old friend of us, okay? So if I look at the graph deformation of this F, in other words, if I use this notation for the graph deformation of this F. If I take this graph deformation, if you look at this, you see that is exactly the deformation we saw before. It's K-versal. So this is K-versal. Can you see what I write here in the bottom? Yeah? This is exactly what you did before. Right? And the main result that we want to discuss now is that the original F is K-stable if and only if the graph deformation of this is K-versal. Okay? So we can make a picture here quickly. Let me make some picture here. So let's look at big F, map big F. So I have here K3. And I can compute the singular set of this map, right? It will be, if I call here U and Y and this X, the singular set of this map will be a parabola like this because it's X equals to 0 and U equals minus 3 Y squared. Okay, so this is a singular set. And so I have the map F here that goes to the space that I call coordinates here, U and W. And if you compute the discriminant of this map, which is the image of the singular set, you get a cusp. This is a good exercise for you here. Then let's look at what are the fibers of this map, right? When you are at the origin, you have the special fiber, right? You get here exactly, if you take U and W equals 0, you get here exactly a cusp in this plane here, right? If you take any Y and W that are not in this discriminant set, you have a smooth fiber there. And if you take a point here, you get as a fiber a curve which has a double point. Okay? So you have here right? And so the fibers of this map describe the family of ICs that we obtain through the K-versal deformation. Okay? Any question? Any question? Well, I think this is the main idea and for the rest of the lecture. And I can skip some things, but more generally, in this example, F was stable, right? But more generally, if we take any S-parameter deformation, which is submersive, then we can compute the zero set of this S-parameter deformation. So VF is F inverse of 0. And so VF is a smooth variety in Ks cross Kn. And I can restrict the projection to the parameter space to this smooth manifold VF, right? So repeating, I have a S-parameter deformation, which is a submersion. And VF, it's zero set. And I restrict the projection. I restrict to VF the projection into the parameter space. What happens then, a little bit more general than here, is that I can compare, can look at this map PF and compare the A classes of this map with the K classes of little f, right? I think take into account that we are a little bit close to the end. But anyway, this proposition says that if f and g are two K-versal S-parameter deformations of two germs F0 and G0 of rank 0, if F0 and G0 are K equivalent, then pi F and pi G are A equivalent. So we go back to the question I posed in the beginning of this part. So I wanted to look at the correspondence between A orbits and K orbits. Of course, I skipped the proof, but we can discuss in the exercise if you want. And and now just to conclude, more or less, we're getting close to the end, it's just to make sure how we do this and that we can do looking at the special type of graph deformation as I just explained it here, right? So then suppose that F is a R parameter unfolding of a K finitely determinate germ, FF, as we did before. To this F, we can associate the graph deformation, right? So we have F, big F, and the graph deformation as before. As before. Then what we saw, or what we want to establish, is that, in fact, of course, we have that dF is an R plus P parameter submersive deformation of F. And of course, there is this connection between F and dF because VDF, which is the zero set of this graph deformation, is the graph of F. And in fact, we can see that this projection can be identified with F, right? Then we have this theorem. A map germ F is A stable if and only if dF is a K-versal deformation of F. Okay? I skip this, I will not give the proofs. But this is what we wanted, because if we denote, then, if we can then relate the A orbits of stable germs with the K orbit of the versal deformation we obtain with the graph deformation, then if I denote by S, R, and P the set of A orbits of stable germs of rank R, and denote by K, R, and P the K orbits of germs from Kn to Kp of rank 0 and K codimension less than or equal R plus P. And we can establish a correspondence between these two sets just by, as I said before, given an F, I make it correspond to little ff. This is well defined in this set from the properties we discussed. This mapping is a bijection, right? And being a bijection, as a corollary, we obtain the result that Roberta mentioned, that if you have F and G stable map germs, then they are K equivalent if and only if they are A equivalent. Right? It's a direct consequence of the correspondence between the sets. And that's it. So, and finally here we have this example again. So in practice, what we have, I think I can use 1 minute more. In practice, what we have, I start with a rank, I can start with a rank 0 germ, right? For instance, or one ideal, for instance, right? Rank 0 germ. I construct the K-versal deformation of it. And from that construction, I can obtain the A-stable singularity, which is K equivalent to a suspension of this one. Okay? Okay, so I just will not give the notion of Kodaira-Spencer map, wow, because I think it's too much, right? I think it's, thank you very much. Any question? Any comment? Any doubt? Okay.
So at some point, you use that the projections are equivalent to give other relation between the functions. So these projections come from a smooth variety, or okay, yeah, that's what I thought.
Yeah, I assume that the K unfolding, K deformation is surjective.
Yeah, of course, yeah. Thank you.
Well, we have an exercise session on Thursday, right? If you have any doubt, any question, okay? Muito bom.
do at least some announcements. For those of you who have been yesterday in the installation session, for those who have made it to the point to really install Oscar, there was a problem in the end. And that problem has been solved. So now there's an updated version of the worksheet 1, where in one command I had to remove 2 quotes and then everything worked. So in that case, please try again. And if you have already installed the official Oscar, then I think it will be better if you first remove the official one and then take the special one as written in the worksheet. And of course, if you have any further questions, you can approach me in the coffee breaks or wherever you see me. I'll be happy to help. And the other announcement that I was asked to quickly make is that we will meet for the happy hour this afternoon at 12 in front of this auditorium. So if you want to come and you, then please be there. And then I think we will have some transportation. Good. So I see we have Anne there. Anne, can you hear us?
Hi, Matthias.
Hello.
Can you hear me?
Yes, we can hear you. Nice
Great.
to have you back. So I just made 2 announcements, and
I heard it.
I think we're good to start.
Yes, and we should start with the slides, please.
Yes. There we go. The slides are on the big screen.
So let me quickly scroll to the slides we had yesterday, because we stopped in the middle. Just let me remind you, we talked about standard basis yesterday to get from ideals to monomial ideals to the leading ideals. That will come up today again. And that's the point where we left off yesterday. Dimension and multiplicity, of course, are not the only invariants that we are interested in and that we want to compute. There are also other invariants, and I use them as the opportunity to introduce you even further to the technicalities of computing in singularity theory. So the next invariant we look at is the Milnor number of a hypersurface. It's well known to you that it is the quotient of, wait, there's something here? Okay. It's the quotient of the power series ring modulo the ideal generated by the partial derivative and taking the C vector space dimension of it. Would you please stay on the slide? Paolo or Leonardo, could you please make sure that the slide is in the picture? Thank you. The geometric meaning of it is that it counts the number of vanishing cycles. That is, if you have your singularity and you perturb it just a little bit, then certain cycles will appear, you know that, and down here on the slide, I have a nice picture of it. You see a D4 singularity on the left, and on the right, you see the fiber of smoothing of it, and you see here the cycles that appear, 4 of them, because the Milnor number of a D4 is 4. Now, let us look at how to compute this. Again, I start with a simple example. It's just the Milnor number of an E6 singularity. And of course, the partial derivatives are x squared and y to the 4th, so we are monomial. So there's nothing else to do than look at the monomial diagram. If x squared is in there, any multiple of x squared is in there, so we can just take away the whole quadrant that we moved to x squared here. That's the blue one that we are taking away. And for y to the 4th, Here in red, we are doing exactly the same thing. Every multiple of y to the fourth will be in here. So we end up with just this part down here, and we can count that we have really 8 monomials that are not in our ideal generated by x squared and y to the fourth. Of course, this was purely combinatorial because we were in the monomial case. So again, this is a problem of reducing to the monomial case that we are facing here. Let us look at the other example that we introduced the last time. It's a 2-coordinate axis and a line meeting them in the points 1, 0 and 0, 1. For ZF up here, we determine the Jacobian matrix. So we take the partial derivatives. You see them here. Now we take a local degree ordering. The picture is coming, Matthias.
Okay.
So we take a local degree ordering. Local degree ordering means we first look at the monomials of lowest degree. In the first polynomial in the Jacobian matrix, you see the monomial of lowest degree is y, and here it's x. So the monomial ideal we assign to it will be generated by x and y, and we get a Milnor number of 1, as we would expect at the origin, with 2 lines meeting transversally. Now, if we choose a global monomial ordering, then we get a completely different leading ideal. We get x squared, xy, y cubed, which gives us a Milnor number of 4. A Milnor number of 4 is a bit puzzling. Let us look at the picture. Of course, we see 3 points where a pair of curves intersect. So we would expect a contribution of 1 for each of these points. But indeed, in the middle of that area here, we have yet another point, the point 1/3, 1/3, where our gradient, where the Jacobian matrix vanishes. And that's the solution for the mystery, how we get to 4 instead of 3. We are looking at the critical points of the map defined by F. We are not looking at the singular locus of the zero set we have in the picture. So we see taking a local or global degree ordering makes a difference. That is, we need to look at that and find out what is the difference between taking local and global degree orderings. On this slide, you first see examples of global monomial orderings, and most importantly, in the first line on the slide, you have the condition for being a global monomial ordering. Because a monomial ordering is global whenever the smallest monomial in the set of all monomials is 1. That is, all variables are larger than 1. Then we call a monomial ordering global, and then our calculations that we do on the computer will correspond to calculations in the polynomial ring. If, however, we are in the situation that 1 is the largest monomial, that is, 1 is larger than any variable xi, then we call a monomial ordering local. And computing in this ordering will mean that we compute in a localization of the polynomial ring at the origin. Of course, there are also situations in which you have some variables which are bigger than 1 and some variables that are smaller than 1. In that case, we talk about a mixed ordering, and for the scope of this talk, there won't be any mixed orderings. There will just be global and local monomial orderings. So let us look at the examples of the monomial orderings. So the first one is lexicographical ordering, which means compare as you would if you look something up in the dictionary. Compare the 2 exponents starting from the beginning until you see the first difference, and there the larger entry will win. For a degree lexicographical ordering, it's a bit more subtle. We look first at the degree of those exponents of those monomials, x to the alpha and x to the beta. And if the degree of the first one is bigger than the degree of the second one, then the first one is bigger than the second one. And only when we get to the case that the two degrees coincide, we'll continue with a lex comparison with the comparison we had up there. And you see, a global ordering means that the bigger degree wins in a degree lexicographical ordering. Now, if we go to local monomial orderings, I just have one example here. Negative degree lexicographical ordering. Here, it's basically the same as above, except that the monomial of lower degree wins. And there's something wrong with the brackets. I have to clean that up later on. In any case, if the degree of x to the beta is larger than the degree of x to the alpha, then x to the alpha will win. So up here, you'll get a leading monomial of which the degree is the same as the degree of the polynomial itself with deck-lex. And with next deck-lex, you get a leading monomial of which the degree is just the order of the polynomial we are looking at, so the lowest appearing degree. This is as an explanation for monomial orderings. Basically, you have to make sure that when you want to do local computations, you use local monomial orderings whenever you fix something explicitly yourself instead of using the localization feature. Whereas when you want to compute something in the polynomial ring, you need to use global orderings. So let's look at the Turner number. This is also well known to you. It gives you the number of parameters you need in a versal family for your hypersurface. And it is defined similarly to the Milnor number, except that this time we factor out the partial derivatives not from the power series ring, but from the power series ring modulo the ideal generated by F, that is, from the local coordinate ring of our germ, which then sums up to factoring out df by dxi to df by dxn and F. Let's get back to our example. Remember we had 3 singular points, and the 3 singular points each have a contribution of 1, and it sums up to the global Turner number of 3. So in the example we had here, the effect of taking an extra generator to our ideal was that we precisely only got those contributions that are on our germ V of F, that is on the representative, because we were not computing in the local ring here, we were computing in the polynomial ring and getting all 3 contributions. In general, as we are modding out one generator more for the Turner number than for the Milnor number, of course, the Turner number can never exceed the Milnor number. But I now take the opportunity to tell you what's happening actually when we reduce. So that picture might be a bit confusing, and that might be the moment, Matthias, where you might draw something to the blackboard.
Yeah, I just recapped that geometric picture, but I need to see your picture again. So can we please, the blackboard the students can see here. Let's have the slides.
And what we are seeing is, first of all, the monomial diagram. And in the monomial diagram, we first take the first partial derivative, so 1 by x, which will be 5x to the 4 minus 3tx squared y cubed with a leading monomial with respect to a local monomial ordering of x to the 4. So I made a square here, and I put in the other monomial also just to tell you these two are linked by the derivative by x. We do the same by the derivative by y. Again, the monomial of lowest degree is y to the 4th, so we put a square here, which means that by our leading monomials of the ideal of partial derivatives, we would just see a square remaining with 16 monomials down here. Now, passing from the Milnor to the Turiner number, we put in f, that's the green one here, and of course we see x to the 5th is a multiple of x to the 4, so we can subtract a suitable multiple of the partial derivative by x, so of the blue line, from the green line to cancel out x to the 5th and get a contribution to x cubed y cubed. We do the same with y to the 4th, and in our case there will be a monomial remaining at x cubed y cubed, which then cuts out another quadrant here starting at x3 y3, and we only have a Turiner number of 15 because we lost another monomial. Matthias?
Yes.
Can I now see your picture?
Okay, yes, I started with the
Oh,
monomial.
you started, but you didn't get to that point. It's on the slides, so maybe we just get back to the slides and then continue with the talk at that point, because now it's time for Matthias to go to his worksheet and to show us the first part of those computations.
Okay.
Your turn, Matthias.
All right. Thank you. So let's find the part of the worksheet where this becomes relevant, or where we pick up on this. This is worksheet number 2. And yesterday we saw the dimension discussion. So here we have computations of the Milnor number, what Anne has said in the beginning. Let's make this a little bigger. The example of the 3 lines, that's how you can quickly write it here in Oscar, the example you see there. And the Milnor number function, I think this is no surprise if you look at what is written in the function. It's just what you saw on the slides before and what you have probably done by yourself at some point. But you see one command which is a little bit tricky, and it's here. I called it, for the time being, singular vdim. And those of you who use singular or who have used singular know the vdim command. And what does it do? It does exactly what was discussed before. It counts points in the monomial diagram, right? So I'm using this here to compute the Milnor number. And I can compute the Milnor number from this hypersurface over there, and as before it was 4, right? So remind that this corresponds to 4 critical points of the function f. And now you can repeat this discussion with local ordering. So here we did what was on the slides before. We compute a leading ideal of this Jacobian ideal, but with a local ordering, as you saw before.
That's the global.
Ah, no, okay, sorry, that's the global case. And the global leading ideal, that was on the slides. And in particular, we should be able to, let's give this a name, lead J, and then we can ask for this dimension 4, and we can repeat the same thing with a global ordering.
No,
with
that's
a
the local one.
Local, yeah, and then you see the leading ideal is quite different, and I think we do not need to run
No.
the vdim command in this case, because everything that is a multiple of x, right, it's gone. Everything that's a multiple of y is gone in the monomial diagram, and here you just have one bullet, one dot that's remaining. So the local Milnor number is 1. And the Turiner number, and the example that was on the slide, starts here. So what do we find? We have the equation here, x5 plus y to the 5th. And we can ask for the ideal defined by this hypersurface ideal, and the partial derivatives of f0. This is this Turiner ideal that you saw before.
Maybe we should stress that for doing the sum, we explicitly need to transform f0 into an ideal generated by f0.
Sorry, I did not get this.
Maybe we should stress at this point that we have to transform the polynomial f0 explicitly into the ideal generated by f0 to do the sum.
Right. If we just
that is important for the users.
We cannot write this, right? Then we add a polynomial with another ideal. It will complain. Good. Let's do that. And we see the dimension is 16. Anna, is this correct?
This is correct. We had a square of length 4 in the sides for the Turiner number of this hypersurface. And
all right.
Now we add another summand.
So let's just have a look at this ideal, right? No surprises here. x5 plus y5, x4, and y4. So in this monomial diagram over here, we see everything that is a multiple of x to the 4. 0, 1, 2, 3, 4. Here comes x to the 4. And now every multiple of this sits here in this big quadrant, shifted quadrant. And that is 0 in the quotient. Same for y. 1, 2, 3, no. 0, 1, 2, 3, 4. Here comes y to the 4. And everything that's a multiple of y to the 4 sits up here. And then we have one more polynomial, which has 2 terms, namely here y to the 5th plus x to the 5th. But they are already in the shadow area, so to say. So we can discard them. And you do the counting. These are the 16 remaining dimensions. Good. And then how did you already discuss this with
yes.
Yes. So now we try the same thing with a modified function, f1. How does f1 differ from f0? It has this additional term in the end, plus x cubed, y cubed. So in the monomial diagram, we have this, and that. And so not everything of f is in the shadow area, right? Also here, y fourth, the partial derivatives are also more complicated. It's not only this term, it's this term and something here. We have seen this before on the slides, just to remind you. And the other partial derivative is something with x4 and something here. But now when you compute a standard basis, a local standard basis, you will see that the orderings are chosen in such a way that some replacements take place, and the final dimension of this algebra, as you see here in this yeah, I need my screen back, sorry. Yeah, thanks. The final outcome of these computations here, number 14, is 15 and not 16. So I should say that this last command, singular vdim, it does this counting in the monomial diagram, but with a local ordering, right? So as you saw on the slides. Maybe we have the definition of, no, it's not here, the definition of this singular vdim local, right? So that's what you had on the slides written in OSCAR. Anne, anything to add?
Just that for both singularities, the Milnor number is, of course, still 16, no matter whether we have x cubed plus y times y cubed or not. Can we get back to the slides, please? Some of you in the audience might have always computed the Milnor number in a different way, and I'll just briefly sketch this approach. So we look at the Newton polyhedron. What's that? So look at F as a power series, and then you mark in the monomial diagram all those monomials where the coefficient is non-zero, so all appearing monomials, and you take the convex hull. That gives you a polytope. Now, you form the union of that polytope with 0 and take again the convex hull. That gives you a new object, K of F, and then you take away the polytope from above from that new one and take the closure of it. Then you get K0. For that K0, the Minkowski mixed volume, which is an invariant of polytopes, then gives you precisely the Milnor number, of course only if F is Newton non-degenerate, which is something I'm not going to go into detail for. But for this construction, I want to give you a drawing. So I've taken here a polynomial with 4 monomials so that there's something to see on the picture. You see, we have x to the 5, we have xy to the 4th, we have x squared y squared, and x cubed y cubed. That gives you a total of 4 monomials. And if we take the convex hull of that, then we get this quadrilateral here, which I named delta of F. Now, we have to add the origin. So, and take the convex hull again. This gives us this object with a blue boundary. And now, from that object with blue boundary, we take away delta of F, and we take the closure again. That gives you the red one. So those lines that look purple are just blue and red, one over the other, and the other 2 lines here in red. And the areas that I shaded in red down here is precisely the area for which we need to take the Minkowski mixed volume in this particular example. So that's the construction. You might say, oh my God, why so complicated? I always took the monomials, put them in the monomial diagram, added a quadrant to them, and then took the convex hull and everything was fine. Yes, you're perfectly right. That's how you can do it. But unfortunately, if you want to do it in OSCAR and make it understandable for the polymake side, which is the polyhedrogeometry side of OSCAR, then please use this construction, because this construction makes sure that in the end you get the right hull operation that you want to have, and you don't get stuck with something of a shape that you didn't expect just because OSCAR, or more precisely polymake, didn't understand what's going on.
I think we can stay on the slides. This is just assistance. Yes.
This is just for the room so that they know where the boundaries are.
Yeah, Anna, I should maybe say that probably it's a little difficult to read because the colors are not so
they are not so bright. Yes.
So heavy contrast. So I thought it might be a good idea to.
Yep, it is definitely a good idea.
But
so
let's
having
stay on
said this, I'm now leaving the realm of hypersurfaces and move on to complete intersection singularities. I assume that in the other talks of the school, you have already seen a lot of stuff on isosingularities, on isolated complete intersection singularities, and probably the Legge-Royal formula popped up for computing the Milnor number of such a singularity. So our setting is we have an isolated complete intersection, which is not a hypersurface. So Q is at least 2. And it is a complete intersection, which is to say that the number of Fi we are seeing here is precisely the codimension we have in Cn. And it has an isolated singularity at the origin. Now, to compute the Milnor number in this way, we have to form several ideals. So first of all, we have to form ideals Jk, which are generated by the minors of size k, which are the maximal minors of the Jacobian matrix of the first k Fi.
Anna, one question. K is Q?
No, K is not Q. K is running from 1 to Q. We need them all.
Sorry,
it's not just one K. It's for each K we are defining that. For each possible K.
Yes, yes, I get it. I was just confused because at one point you said maximal minors, but
it's the maximal minors of this Jacobian matrix back here. But this Jacobian matrix only takes into account F1 to Fk.
Ah, yes, okay. Yes.
So the maximal minors are the minors of size k. Just because we run out of Fi.
Okay. So you filter the generators of your ideal. You first take only 1, then 2, then 3, and so on.
Yes, and Ik is an ideal generated by the k minus first original generators plus that ideal Jk. So for the derivative, we take the first k Fi into account, but as generators, we only use F1 to Fk minus 1 up front for the other part. And those ideals Ik are also subject to a further condition. It's a condition of having finite co-length in our power series ring. So power series ring modulo ik needs to be finite dimensional for all k appearing. If we satisfy the setting, then we can compute the Milnor number of our isolated complete intersection singularity at the origin as the alternating sum over the dimensions of the power series ring modulo our ik, modulo the ideals we have just defined. That looks a bit complicated, and I think the most crucial part of it is the finite co-length condition. So let us look at the finite co-length condition once again. And that is here on this slide. I've taken the simplest of the simple codimension 2, so space curve singularities. It's an S5 singularity from Justice list. We had that already yesterday. And now I'm taking the original generators. F1, I first choose as xy, and F2 as x squared plus y squared plus z squared. And then I try the construction. And I see my ideal I2 will be generated by xy, and then by the minors of the Jacobian matrix of the two. And those minors are xz, yx, and x squared plus y squared. Look at that ideal, and you see immediately that no pure power of z can appear in this ideal, which means this is not of finite co-length. Now you might say, oh no, the formula fails, I cannot apply it. But if we choose F1 and F2 differently, if we just exchange them in their roles, then we get a similar ideal, but it's x squared plus y squared plus z squared up front. Then we have xz, xy, and x squared plus y squared from the minors. Now, of course, x squared plus y squared cancels with the part up front. And we also have a z squared in here. And this is indeed of finite co-length. Of course, what helped here in this particular example doesn't help in general, but it helps to take a sufficiently general linear combination there. Was there a question in the audience?
Yes. We have one question.
I was wondering if it would help people to think of what you're doing in this way. You start with an ISIS, and then you want to build a whole chain of ISIS. So you start with a hypersurface, and then you take the next one as codimension 2, but it is a hypersurface inside the first. And you keep going all the way down until you get to the ISIS that you want.
Yep. That's a good geometric way of phrasing what's going on up here.
So
we are always taking one of the FI.
Okay. They're the minors that are associated with these intermediate ISIS going all the way down.
Yep.
Okay, thank you.
That's a good way of describing it. Now, for computing the T1, or the Turner number of our isolated complete intersection, we are basically in the same situation. We have a complete intersection space germ generated by F1 to FQ, so it's of codimension Q. And then we can easily compute our T1 as C of X to the Q. Think of it as all the positions where we can do a perturbation, modulo the ideal at the generators of the ideal at each of the possible positions, plus now the ideal generated by the columns of the Jacobian matrix, so by the partial derivative of the Fi, taken as a tuple. Note that this is a computation with modules instead of the computation with ideals that we had before, all the way to the last slide. Here's the first time we are dealing with free modules. And also note that here we don't have some kind of condition on the generators of what we factor out like we had on the previous slide. So from one point of view, it's an easier calculation because we don't have to look at some general combination. From the other perspective, it's something new, it's modules. And now I think it's time again for Matthias.
All right, thank you. So we need my laptop on the screen again. Thank you. And I should make this even bigger to be readable. So let's try to carry out this example from the slides. I should maybe say Le is written with a hat on the E, but I didn't find that hat. So apart from that, will you see there go the equations from the slides here for this ideal. And as was explained by Anne, we need to choose random ICEs that contain the original one as the final step, or as was remarked by Terry. Then we need to do random vector generation in OSCA. And I brought you one example here in here. So what does this do? It gives us a 10-element vector, or a vector in Q to the 10th. And the entries are fractions, so elements of QQ, with both numerator and denominator within the range from -100 to 100. And we can use that to compute the Milnor number of our ICEs. So let's define our ICEs. 3 variables, 2 equations. When we're lucky, then the dimension of our ideal is 1. And OSCA tells us that this is indeed the case. Then next thing we can check is, do we really have isolated singularity? And the answer is yes. As you can see, the geometric locus, the geometric singular locus is only the origin. Good. So now we need to construct the successive ICEs hypersurfaces, one being a hypersurface in the other, to arrive at the final ICEs that we have defined. And we do this by passing to a random linear combination of the generators of our ideal. Right? So what do we see here? H is a sum. It's a sum of a vector, and it multiplies C with G, where C runs through this random vector before, and G runs through the generators of I. And then we should get the same ideal as before, only with different generators. So let's...
You just took a polynomial instead of an ideal.
Sorry, say again?
You just took a principal ideal instead of the ideal generated by 2 generators.
Ah, yes, that's true. I do a candidate for the hypersurface in C3 that contains our ICEs. So let's check. I1 is subset I1 I. Okay, yeah, we're good. So let us verify that this other bigger ICEs is also has isolated singularity and is of the correct dimension. It's all fine. the random choice was sufficiently random. So let's compute the Milnor number of this ambient ISIS, H. H was the generator of this I1, right? It's 1. And if we want to look closer, I don't know if we probably come back to this later in the course. We can ask even more information about the singularity. So this is really the A1 singularity, but that will probably come later. There's only one singularity with Milnor number 1, one hypersurface singularity. So this was expected. Okay, here comes the block which is really at the heart of the Legreux formula. It's these complicated expressions that we had on the slides. And it computes this intermediate Morse points of Morsification of one hypersurface in the other ISIS that was on the slides. We get 6. And if you compare all this complicated code with the complicated formulas on the slides, then you eventually find that what you have to do when you follow the recipe is take the 6, subtract the 1, end up with 5. And there we go. That's the Milnor number of our ISIS. Questions? Good.
How much time do we have left?
I think we're over, right?
I think we are over time. I think the modules have to stay for Monday.
Good. So.
And maybe that is the moment to say that tomorrow we are on the schedule with a double slot, but that double slot will not be for a talk. I heard from Matthias that you successfully installed, or less successfully installed, Oscar on your computers. In any case, you should be all set for a hands-on session tomorrow. And the hands-on session will, of course, not be recorded. And the only way to learn a computer algebra system is to really work with it. That's why we scheduled a hands-on session.
All right, so tomorrow, everybody bring their laptops and we will do some serious exercise.
And of course, that will not be recorded. So
nobody needs to
feel ashamed.
The
most stupid question tomorrow will be the question you don't ask. That gets you stuck. There are no stupid questions tomorrow.
All right, then we close today's session, I think. Thank you.